Welcome everyone. In this video, we are going to pick up our discussion of chemical equilibria with a discussion of the more quantitative aspects using the topic of equilibrium constants. Now, being able to quantify chemical equilibria is going to be of tremendous value in a variety of contexts, and we're going to be discussing those throughout the course. In this lecture video, we want to focus in on three core learning objectives to really help us understand chemical equilibria from a quantitative perspective. So the first learning objective involves what we call reaction quotients. We're going to talk about what reaction quotients are and how we can understand and derive a reaction quotient from a chemical reaction equation for both homogeneous and heterogeneous reactions. We're going to also talk about how we can calculate values of reaction quotients and equilibrium constants using concentrations and pressures. We'll find that concentrations or pressures, one might be more useful in certain contexts than another, and we'll see how we can go back and forth, and of course, when to use one over the other. And finally, we are going to talk about how we can relate the magnitude of an equilibrium constant to the properties of that chemical system. Okay, so a quick recap here. Recall from our last lecture, we were exploring this NO2 decomposition reaction. We saw how if you were to say start a reaction off that was in a little reaction vessel that was composed entirely of N2O4, a clear container, we would see this decrease in concentration of N2O4 as the reaction progressed, increase in concentration of the resulting products. And this would, again, just represent that forward reaction occurring. And over time, the concentrations of both the reactants and products will achieve a constant value. And once the concentrations are no longer changing, we say that equilibrium has been achieved. Okay, so now the question comes in, how could we quantify the status of a reaction with a single number? For example, if we were to pick some arbitrary time t, we would want to be able to say quantitatively, what is that reaction doing? Where is this reaction on its path to equilibrium? And perhaps the question could be answered by saying, hey, well, the reaction is already at equilibrium, or perhaps it's at some other point. We want to be able to quantify this and understand this better. And so the answer to that question comes in the form of what we call the reaction quotient. We oftentimes denote the reaction quotient by a capital Q. So to define the reaction quotient, I want you to consider a generic reversible reaction where you have A and B coming together to form C and D, where we're using lowercase letters here, M, N, X, and Y to denote the stoichiometric coefficients. We define the reaction quotient in terms of concentrations, and I'm using a little c here to denote molar concentrations. We define it as a ratio. Right? Again, going back to our analogy of the folks that are on the shore and in the water, we set up this little ratio, right? We are defining a ratio of products, concentration of products specifically, C and D in this case, over concentration of reactants, A and B in this case, where each one of those concentration terms are raised to the power that's given by their stoichiometric coefficient. Now, if the reactants and products are in the gas phase, you can alternatively define the reaction quotient Q in terms of partial pressures. When we do that, we use a little subscript here to denote that you're talking about reaction quotient in terms of partial pressures, where we have partial pressure of products over partial pressure of reactants. And once again, we are raising each one of these partial pressures to using the stoichiometric coefficient in that balanced chemical reaction equation. Okay, so that's it. That's our main definition that we're going to be using for this lecture. Now, I want to point out that these equations, the reaction quotient in terms of concentration or pressures, are a simplified form of a more rigorous expression that uses relative values. And so there's some complexity here that is simply beyond the scope of the course you're more than welcome to reach out to me and we can talk about this in more detail. But suffice it to say, for right now, we will effectively be able to quantify and understand equilibrium dynamics using either equations 1 or 2 and effectively ignoring units. So pick whatever unit you want for pressure, be consistent, use your concentration and molarity, and you will be good to go in terms of solving problems. But keep in mind that, yes, we must disregard units here. All right. That said, we're ready to jump into our first example. So let's look at an example here, a very simple reaction involving O2 reacting to form O3, ozone. So molecular oxygen forming ozone, and of course this is a reversible reaction. We have our stoichiometric coefficients highlighted in green and red here, denoting O2 and O3 respectively. And we can say, okay, what would be the concentration-based reaction quotient for this reaction? Well, it's concentration-based, so we're going to use QC. We're going to write QC, and then we're going to look at our products, which is O3 in this case. We're going to put products over reactants, and because again it's concentration-based, we're looking at molar concentrations, and then we are going to use those stoichiometric coefficients in the exponent. Okay, so hopefully that's relatively painless. We've now given a single number Q to describe the state of this reaction as a reaction quotient. So here's another little quick example that's a little bit more complicated, but we'll see that the exact same principles allow us to write down arbitrarily complex reaction quotients. So in this example, we've got a more complicated reaction with some significantly larger stoichiometric coefficients. And now we've got 2 reactants, 2 products, and we write it all down. So the products here, NO2, H2O over reactants, ammonium and molecular oxygen. And then we're going through and bringing down all those stoichiometric coefficients as exponents. Okay, so that's step 1 here. We hopefully are comfortable with this idea of a reaction quotient, defining as such, and writing one of these down for any arbitrary reaction. Now let's take a look at what Q is actually telling us. Okay, so as you could imagine, Q is expressed in terms of this ratio of concentration raised to powers given by stoichiometric coefficients. So what does that mean? Well, it means that as the reaction progresses towards equilibrium, the numerical value of Q changes. So if we consider yet another example of a reaction here, SO2 and O2 going to SO3 gas, we can begin with writing down QC. And so if we were to look at a scenario where a mixture is comprised of only reactants, the products over the reactants in this QC expression is going to give us a value of 0, because if we only have reactants, then that means there's a 0 concentration of SO3 here. So you have 0 squared over whatever our initial concentrations are. Well, it's 0, right? And so, of course, QC, a QC of 0, tells us that our reaction mixture only has reactants. Now, as the reaction proceeds, a couple things are going to happen. First, reactant concentrations are going to decrease. Okay? So as the reaction proceeds, we're using up reactant, the concentrations are going to go down. So the denominator is going to go down. And of course, the product concentration is going to increase. Here, the denominator is going down, the numerator is going to be going up. And so decreasing the denominator, increasing the numerator is going to have the effect of increasing QC. So QC increases. Now, remember, eventually at equilibrium, concentrations become constant. All right? Let's put that in there. Remember that at equilibrium, concentrations are going to become constant. All right, so if you reach constant concentrations at equilibrium, what's going to happen to our QC? Well, hopefully you guessed it, that QC is going to go to some fixed value, right? We'll call that fixed value K. So to appreciate this, I've taken our same exact scenario and we've added a couple plots down at the bottom here to help us explore graphically what's happening in terms of the changes in concentration. So again, remember, our scenario one, our reaction starts off with only reactants, right? And so only reactants are present. So our product, SO3, is at a 0 concentration here. And so our QC value is going to be 0. So if we're looking at our reaction quotient on the y-axis, right, reaction quotient K, what we see here is initially we have no product and our reaction quotient is 0. Okay, now as our reactants start to get used up, their concentration, of course, goes down. And as their reactant concentration goes down, the product concentration goes up. As we saw in our discussion on the last slide, that means that our reaction quotient, QC, is going to rise. So one more time, the reactant concentrations decrease, product concentrations increase. Because of our products over reactants ratio here in the definition of QC, that means that the reaction quotient is going to increase. And as the reaction proceeds, we are eventually going to hit equilibrium where the ratios, where the concentrations of our reactants and products become constant. The point at which that occurs corresponds to chemical equilibrium, which over here is going to be seen as that reaction quotient no longer changing in time. It will increase until it flatlines and becomes equal to K. So K is a fixed value for a given reaction under certain conditions that basically defines, it's defined the same way as QC, but it is the ratio of products and reactants with this same form, appropriate exponents, at equilibrium. Okay, and now I'm going to define that again here in a minute. But what I want to do first, before we dive into more of a discussion of K, is I want to consider an alternative scenario. Let's call this scenario 2. In scenario 2, let's suppose that we have our reaction here, but our reaction is now starting off with only product being present. So only product is over here. And if you have only product and you plug this scenario into our reaction quotient, then that means we have a 0 down here in the denominator, which of course is undefined. This sort of function would approach infinity. And so we're going to kind of highlight that here by, just showing our plot of QC as a function of time going up to infinity. And of course, now over here on our concentration plot, we're starting off with some amount of product and we have 0 reactants. And so as this reaction proceeds, product concentration will decrease. We're going to start using up our product. Reactant concentration is going to increase. We're going to start forming more and more reactants. And if we are decreasing product concentration, increasing reactant concentration, then that means we're going to be decreasing our value of QC. It's going to start coming down from infinity. Okay? And of course, as soon as we have any measurable amount of SO2 and O2, it'll of course no longer be infinity. It'll be some number, and that number will continue to decrease until we eventually reach equilibrium, where we have constant concentrations of reactants and products. The forward and reverse rates are equivalent. And if we plot this over here on our plot of Q, reaction quotient, as a function of time, we see something like this, where at this point, this equilibrium point, all right, we are finding constant concentrations at equal rates of forward and reverse, and our QC becomes equal to K. So with those two scenarios in mind, summarized here, we're now ready to define our so-called equilibrium constant. So the constant value Q that's exhibited by a system at equilibrium, right? That's this range right here, this range right here. And again, it doesn't matter whether or not we started off, with all, reactants or all products. And either way, we are coming up or coming down, and we are eventually going to reach, right, this fixed value of K. So K is simply equal to Q at equilibrium. Now I want to highlight here on this plot, the value under both scenario 1 and scenario 2 for this given reaction of K is the same. And we actually codify this in the so-called law of mass action. The law of mass action states that the reaction quotient for a system at equilibrium is constant at a given temperature. Again, whether you're starting off with more reactants or more products, right, in different scenarios, right, Q will be changing, but K will be the same for both, again, at a given temperature. So this allows us to talk about reactions in terms of what is their equilibrium constant K, right? And we can agree upon some temperature or make that temperature explicit in that discussion. But once we've done that, we will have some fixed value K that will describe the equilibrium of that chemical reaction. All right, so let's take a look at what this allows us to do and consider the following example. We can evaluate a reaction quotient for a given reaction. Let's go back and look at our favorite reaction now, NO2 and N2O4, our favorite reversible reaction at least. And let's suppose that we start off with a situation here that has with 0.10 moles of NO2 added to a 1 liter flask at 25 degrees Celsius. And let's suppose the concentration changes so that at equilibrium, NO2 concentration is 0.1016 molar. And the concentration for N2O4 is 0.042 molar. What we want to determine here is what is the value of the reaction quotient before any reaction occurs, right? So before any reaction occurs, we are just going to start off by adding that 0.10 moles of NO2. So we're going to be entirely on the reactant side. So remember that for all equilibrium calculations, we disregard units. Okay, so we're going to be writing out these expressions using equations 1 and 2 on the previous slide, whichever one's more convenient. In this case, we're talking in terms of concentration, so we'll use equation 1, which is our QC expression. And so all we need to do is calculate concentrations under this first set of conditions where you only have reactants present. So we're told in the problem that we're starting off with 0.1 moles of NO2 in a 1 liter flask. So the concentration of NO2 is just going to be 0.1 molar. We don't have any product yet. And so the QC value is going to be concentration of product or reactant. There's no product here. And so we have a reaction quotient of 0, just as we saw before in scenario 1. Okay, now let's look at the same problem, but now let's consider something else. Now let's determine what the value of the equilibrium constant is for this reaction. Now for this, what we are going to have to use is our second piece of information. Remember, the problem tells us that at equilibrium, we have the following concentrations. Okay, so we know our equilibrium concentrations. Okay, we're going to use these equilibrium concentrations to calculate QC. So remember that at equilibrium, QC and KC are the same, right? QC becomes that equilibrium constant. So all we have to do here is calculate K by saying, okay, what's the definition for the reaction quotient? We're going to have products over reactants. And we can highlight this just to make it clear. We've got our product, right, over our reactant. And then we don't want to forget that we got to raise each of these terms using the respective stoichiometric coefficient. And then we're going to just say, hey, look, I know that at equilibrium, my concentration of N2O4 is 0.042. Okay, so we're going to plug in that value. And we know that at equilibrium, the concentration of NO2 is 0.016 molar. So we're going to plug that in right here. Again, remembering to keep that exponent. And once we set this up, and again, I'm setting it up without plugging in any of the units, right? Because of course, you know, we're talking about relative concentrations here, and so we basically just drop the units, don't think about the units, and we come up with a value of 1.6 times 10 to the second. Okay, so now that hopefully we're comfortable building up reaction quotients and thinking about the equilibrium constant, what I want to do now is start to dive into a little bit greater detail of how these numbers allow us to understand the state of a reaction and what direction a reaction is moving in terms of forward or reverse direction. And also understanding, okay, we've got this value of K and the equilibrium constant. So what does this mean? What does it mean that K is a constant value for a given reaction at a given temperature? All right, let's start with that second point, Kc. So Kc, if we want to interpret what that equilibrium constant Kc means, Kc is explicitly reflecting the composition of a reaction mixture at equilibrium, right? The equilibrium constant. All right, so let's look at another example reaction. In this case, it's a reaction of CO2 and H2O to form, or CO and H2O to form CO2 and hydrogen gas. All right, so let's consider three different mixtures, okay? If we have a mixture here, mixture one, mixture two, mixture three, with different compositions, and we consider this as the initial state before a reaction is occurring, right? We can say, okay, the mixture one, we're going to start off with CO2, shown here in red. Let's see if I can get these highlighted appropriately here. All right, so CO2 is right there. And then we will have H2O shown in blue. And we have CO2 shown in green, and then orange for H2, all right? So if we have an initial reaction mixture that's entirely reactants, all right, entirely reactants, then of course our reaction quotient will be 0. If we have a reaction mixture that is entirely products, both products here, CO2 and H2, then of course our reaction quotient will be infinity. And of course, if we make some point in between where we have some measurable amount of both reactants and products, then the reaction quotient will be some number. And you can plug in this number, and I encourage you to do that as maybe a little homework problem. Check that you can in fact use these four given numbers for the concentration at the beginning of this reaction, see if you can get this reaction quotient 0.00446. Okay, so these are three different mixtures, three different starting points, all reactants, all products, mixture of all four. Now, what happens at equilibrium? Well, at equilibrium, obviously reaction rates are constant, the concentrations are constant, so we can define new constant concentrations, and we can determine these. And let's say over here, this work has been done, we have our same three mixtures at equilibrium for this reaction. Given these initial reaction conditions, you will come up with, well, first off, a mixture of all of reactants and products in all cases, okay? So if you had all reactants, well, then now you're gonna have less reactant and now some product there. Of course, if you had all product, well, now you're going to have less product, and you're also going to have some reactants present. And of course, similar sort of thing here, you're going to see, for the mixture, where you started off with some mixture of reactants and products that wasn't at equilibrium. Now you're going to have a new mixture where they will all be at equilibrium. So notice in all these three mixtures, you have very different concentrations of individual reactants and products. That's all comes from how much you started with of each. However, for all three of these mixtures, the reaction quotient at equilibrium will be the same value. And once again, I encourage you as homework here to use the Q reaction quotient expression for this reaction here and verify that these three sets of equilibrium concentrations do in fact all give the same value K. Now, the neat thing is that we can look at K and actually just by looking at the numerical value of K, get some insight into what's happening in this reaction. Specifically, if you have a large value of K, what that means is that the equilibrium is going to be favoring products, right? Because remember, it's products over reactants. A large value of K means the concentration of products is higher. So at equilibrium, you are going to have more products. Conversely, if you have a small value of K, that means that the equilibrium will be favoring reactants. And finally, I want to make an important note here that it doesn't matter how big or how small K is, how much products or reactants are favored. The value of K does not say anything about how rapidly equilibrium is achieved. Right? Some reactions could take millions of years to achieve equilibrium. Others could reach equilibrium in fractions, tiny fractions of a second. And of course, the rate of reactions is the subject of exploration in our topic, reaction kinetics. So feel free to jump over to that unit if you'd like to refresh your memories on talking about reaction rates. All right, so now that we have this interpretation of our reaction equilibrium constant, what I now want to do is look at an example of how we can use this information to predict the direction of a reaction given some initial state. So let's turn again to our example here involving CO2 H2O forming, or CO H2O forming CO2 and hydrogen gas. As we saw in the previous slide, the equilibrium constant for this reaction at some specified temperature is 0.64. All right, again, unitless. Now, let's say we start off with some initial concentrations of all these reactants and products given to us right here. Right? We can start off by defining our reaction quotient. Again, it's going to be our products. All right up here, products over reactants. And we can come through, everything has a stoichiometric coefficient of 1, so there's no powers. We can just go through here and write down all of these values. Plug it in, and you will find that the QC value under these reaction conditions is 0.040. Now, if we compare QC with KC, we of course see something quite important right off the bat. That value of QC is very clearly less than the value of KC. There you go. It's less than the value of KC. And so what that allows us to do is predict the direction of a reaction by just simply comparing the relative values of QC and KC. So specifically here, if you are comparing QC with KC and you find that QC is less than KC, then it turns out the reaction is going to proceed in the forward direction. Why? Well, if the QC is smaller, which is the case that we have right here, then that means that once the reaction reaches equilibrium, we need to see the Q value needs to increase, which means the products need to gain larger values, increase in concentration. The reactants are going to decrease in concentration. All right. And of course, the converse would also hold. If you had Kc is great or Qc is greater than Kc, then we'd have to make the opposite argument and argue the reaction will proceed in the reverse direction. So Qc being less than Kc is a very important observation here that allows us to say, hey, look, this reaction is going to proceed in that forward direction. Okay, so now that we have this under, we can talk about Q and K. We can understand properties of a chemical reaction, predict the direction of change. One next point that we need that's very important to consider, given the broad spectrum of chemical reactions we're likely to encounter, are situations where you have chemical reactions that involve reactants and products that might be in the same or different states. We've been looking at situations where, for example, everything's in the gas phase, or maybe everything's in the liquid phase. What happens if that doesn't hold? Okay. In order to appreciate this discussion, we need to talk about the difference between so-called homogeneous and heterogeneous equilibria. So first up, let's talk about homogeneous. So homogeneous equilibrium is one in which all reactants and products and any catalysts, if we're using them, are present in the same phase. So remember, homogeneous, the same phase. So this could be gas, liquid, what have you. So examples like what we've been previously exploring up to now in our discussion of dynamic equilibria is situations where you either have aqueous solutions or gas phase solutions, everything's in the same state. So one example is the C2H2 reaction with Br2. Again, everything's happening in an aqueous solution. I2 molecules with iodide forming I3 minus. Again, everything's in the same phase, right? And remember, if we have AQ down there, then in fact, aqueous solutions, we're talking about water being the solvent. So everything's just happening in water. All right, and so it's important to keep in mind here that, okay, the fact that we have AQ being written here means, yes, water is the solvent, but because water is the solvent means it's not showing up in the Kc expression, or Q for that matter, okay? It's simply the medium in which a reaction is occurring. We don't explicitly include water in an equilibrium expression if it's just the medium in which the reaction is occurring. Of course, that begs the question, what if what if water is a reactant or a product? It's not just a medium anymore. Well, the answer to this question might be a little surprising. So I want you to pay close attention to this slide here. So in both of these cases, right, we have two reactions occurring in aqueous solution. So water is the medium, but the reactant species is reacting with that medium. Water is a reactant in both cases here. It turns out that water is not included in the reaction quotient. All right, so this could be a little surprising. So remember how I told you that when we're developing these Q or Kc expressions, we're talking about relative concentrations. And I told you just basically ignore units, yada, yada. So it turns out that because you're using these relative concentrations, the relative concentrations for liquids and solids are 1, and so they don't need to be included in this expression. And so the rule of thumb that you need to remember here, again, we don't need to go into the details of what am I really talking about here. Again, talk to me during office hours if you'd like to learn more about that. The rule I want you to remember absolutely for the purposes of this class is to only include concentrations or pressures for terms that are in the gaseous or solute species, okay? So liquids don't show up. Solids won't show up in that equilibrium constant expression. Okay. Now, homogeneous equilibrium is, of course, only one type of equilibrium, we could, of course, talk about the other type of equilibrium, heterogeneous equilibrium as well. Now, before we get into that, I want to touch upon one important point that's going to allow us to just sort of facilitate our conversation when we're moving, starting to work with substances that are in different phases. So you remember we saw how we could express the equilibrium constant either in terms of concentrations or pressures when we're dealing with gases. So let's take a minute here real quick and see how we can relate equilibrium constants expressed in terms of concentration to those expressed in terms of pressure. So we can start going back and forth between these two quantities. So to appreciate this, I want us to first write down one of our favorite one of our favorite equations, probably from general chemistry, PV equals nRT, the ideal gas equation. All right. So we know we can express equilibrium constants in terms of concentration or pressure. Well, remember, we can use PV equals nRT to basically change or express pressures, partial pressures, in terms of concentrations. Right? By just rearranging here, we get this concentration times RT that allows us to figure out what that partial pressure P is. All right, now, if we consider a gas phase reaction, again, going back to our generic A and B going to C and D, we can express this gas phase reaction in terms of partial pressures and define an equilibrium constant Kp as such. Okay, this is just going back to equation 2 from our earlier slide. So plugging in for equation 2, the reactants that we're dealing with here, A, B, C, and D, we get equation 3, which is just Kp for a specific reaction at hand. Now, every time we see a partial pressure, we know that we can use that ideal gas law to express that partial pressure in terms of concentration times RT. So let's do just that. Let's change out PC with the concentration of C times RT. Change out partial pressure of D with the concentration of D times RT. You do this for everything, and then what you do is you actually end up with, highlighted in yellow here, a collection of terms that are all concentrations, and then another collection of terms highlighted in orange here that are all a collection of RT terms, again, where everything is raised to the appropriate power based on the stoichiometric coefficient in that balanced chemical reaction equation. So we can put all these terms together. This highlighted in yellow here is nothing other than just Kc, and everything over here highlighted in orange is just RT raised to some power. And that power is simply going to represent a difference in those stoichiometric coefficients between those products and reactants. So it's the products minus the reactants stoichiometric coefficients, which we oftentimes denote by this little delta N term here. Now, I apologize. I see in the lecture slides here, I'm using N in kind of a confusing way because N here is the stoichiometric coefficient for one of my reactants. And of course, what I mean here when I'm talking about delta N is just how the difference in those stoichiometric coefficients between products minus reactants. So I apologize, we'll change that in a future revision here. Add a little note in there, right? And of course, stoichiometric coefficient itself is not changing. Okay, that means we have our relationship. Our relationship between Kc and Kp is as follows, where delta N is the difference in the molar amounts of products and reactants in that gas phase. All right, so to work through a quick example, make sure we're understanding what we're doing here. If we want to write down an equation relating Kc and Kp for a given reaction equation, the first thing you want to do is figure out the number of moles of gas on the product and reactant side. In this case, the products, we have 1 and 1, got a total of 2 moles and 1 mole on the reactant side. So calculating the difference, products minus reactants, we get a 2 minus 1 is 1. And of course, if you just have 1, that means our power here is just 1. So Kp is going to be equal to Kc times RT. All right, or again, R is just that gas constant. Another quick example, again, going back to a previous example that we looked at with the gas phase reaction involving CO and H2O, forming CO2 and H2. In this case, we have 2 moles of reactant, 2 moles of gas in the reactant, 2 moles of gas on the product side. So in this case, the delta N is going to be 0, 0, 2 minus 2. And so Kp is going to be identically equal in numeric value to Kc. And of course, both are unitless. All right, and then one final example here. In this case, you're actually having a situation where you have more gas molecules on the left-hand side. We want to find the Kc to Kp expression for this reaction. Now, products has 2 moles, right? We've got 3 plus 1 for our reactants. So the delta N is going to be products 2 minus reactants 4, or minus 2. So now Kp is going to be equal to Kc RT raised to the minus 2 power. So what I'd like you to do now is, and I'll leave it as an exercise, is solve a problem such as this. If I give you Kc, right, I tell you Kc for some reaction, in this case it's 0.28, and I tell you the temperature at which we are measuring this equilibrium constant, I want you to be able to calculate what Kp would be at this temperature, right? So of course the steps involved in this process will be first deriving that relationship, as we did in the previous example, between Kp and Kc, and then using that relationship and the given temperature to solve Kp explicitly. All right, so go ahead and do that one as homework. We're now ready to move on to our final topic for this mini lecture, which will be that topic of heterogeneous catalysis as promised. All right, so now that we've talked about equilibria relating Kp, Kc, gas phase, liquid phase, and some of the nuances there, let's put these pieces together and first of all define what heterogeneous equilibria is. So heterogeneous equilibria involves reactants or products in 2 or more phases. So you could even have more than 2, but we're talking something maybe in an aqueous phase moving into a gas phase, or aqueous phase moving into a solid phase, or vice versa. And so there's a whole bunch of examples here, and the take-home message is going to be pretty clear, but it's important to look at it from a number of angles. So first of all, when you were writing out a reaction involving a solid or a liquid, remember we talked about in our discussion of homogeneous equilibria, solids and liquids do not show up in the equilibrium constant expression, right? They simply do not show up because we have, in our more detailed examination of that equilibrium constant expression, relative concentrations, okay? So the relative concentrations are 1, they effectively disappear. So if I'm writing out a reaction where, in this case, a solid lead chloride is dissolving in an aqueous solution, you actually see an equilibrium constant expression that is just the product of the reaction products. Okay, so the mathematical product of the concentration of those reaction products. And similarly, Kp in this case, well, it doesn't make sense to talk about Kp because there are no gases. Okay, so there wouldn't be any reason to bring it up. In this reaction, we have a solid reacting with a gas to form a new solid. All right. Well, again, solids do not show up in the equilibrium constant expression. So the equilibrium constant is simply 1 over the concentration of that single reactant that we have that is in the gas phase. And of course, since it's in the gas phase, we could express this equilibrium in terms of a Kp as well. And finally, a solid reacting with a gas to form a new gas, we're going to see a product and a reactant that's a gas. Since they're gases, we could express in partial pressures. But once again, because carbon in this case is showing up as a solid, we will not see this in that equilibrium constant expression. Okay, so take-home messages here. We've defined Q, this reaction quotient. We've related that to essentially a measure of the status of a reaction, and we can predict the status and direction a reaction will go by comparing Q with the value of K, which of course K is that ratio Q under equilibrium conditions. And we've seen how to write out these expressions for both gas phase and aqueous phase situations, and considering both homogeneous and heterogeneous equilibria, where reactants are all in the same phase for homogeneous or conceivably different phases for heterogeneous reactions. Now, in our next lecture video, we are going to take the next step of looking at how equilibrium systems change when you introduce some change in the environment.